Hi everyone. This lesson is about optimization, which is to find the maximum or minimum of a function. In finance, we would like to maximize returns or minimize risk. In statistics, we would like to maximize likelihood. And optimization is a core part of a lot of the things that a risk manager has to do. We're going to be focusing mainly on the minimizing of functions, and that doesn't cause any real loss of generality because to maximize a function f is essentially equivalent to minimizing minus f. We'll have a look at various methods for doing so, but not at a very technical level. You will have to become familiar with quite a few of the optimization routines that MATLAB provides. As an application, we'll look at linear and nonlinear regression. So as I just said, we'll have a look at various approaches to optimization, but we won't get too technical, we won't go too deep. We'll focus on minimization, and as I already said also, that's no loss of generality because to maximize a function is equivalent to minimizing minus f. F has a maximum where minus f has a minimum. The general type of optimization problem that we look at is going to be of the following form. We're looking for a value x star, which is the argument which minimizes the function f, subject to the constraint that h of x must be less than or equal to 0. Here the objective function is a function from r to the n to the reals. In other words, x is a multidimensional vector, could be one-dimensional. And the inequality hx less than or equal to 0 is a set of constraints which might be empty. When there are no constraints, for example in maximum likelihood estimation that we will do later, we speak of unconstrained optimization. Here's an example from elementary calculus. You're required to find the dimensions of a cylinder whose surface area is a minimum, subject to the constraint that the volume is equal to some constant v0. In other words, you have to find the radius and the height which minimize the surface area. The surface area of a cylinder is given by 2 pi r squared plus 2 pi rh. In other words, the area of the two ends of the cylinder and the side of the cylinder. And the constraint is that the volume, pi r squared h, must be equal to the v0. In other words, pi r squared h minus v0 must be both less than 0 and greater than 0. So the constraint that pi r squared h is equal to v0 can be written as two inequalities, which makes it a problem of the form shown here. Most optimization routines are search algorithms. In other words, they start from an initial point and they search the solution space in an intelligent way, but usually they're only able to locate local minima and not necessarily the global minimum that you're looking for. Most routines are iterative. They use a vector of initial parameters, which is an initial guess, say, of the minimum, as a starting point, and then they start looking. A hopefully better estimate is then obtained as they go along, and then that is used as a new starting point, and the whole procedure is repeated. Then usually a local minimum, which is close to the initial guess, is obtained. To find a global minimum, you may have to start a routine from many initial vectors, many initial guesses, and even then you cannot be sure that the global minimum has actually been located. For functions of one variable, one can find the global minimum simply by graphing the function and looking where it is. But as soon as you have 3 or more variables, graphing the function becomes very difficult. It is therefore important to play around with many initial parameters to find what might be the global minimum. For one-dimensional optimization, in other words, optimizing functions of one variable, one can find a root-finding algorithm to locate the minimum of a function f. A root algorithm such as the bisection method or Newton's method that we covered earlier on. The reason for this is that if f has a minimum at a point x star, then the derivative of f is 0 at that point. In other words, the minimum x star is a root of the derivative f prime. Another way is the so-called Brent's method, which is a one-dimensional optimization algorithm that combines interpolation with a search. Roughly, if we start with 3 points, x1, x2 and x3, which are ordered so that x1 is less than x3 is less than x2, and f of x3 is less than f of x1 and f of x2, then we know that there is a local minimum between x1 and x2. x3 is just an estimate of this minimum. Nevertheless, we can do better by interpolating a parabola through the 3 points, x1, x2, and x3. And then the minimum of that parabola is going to be a new estimate of the minimizer of f. Recall that if a parabola is given by ax squared plus bx plus c, then the minimum is at x equals minus b over 2a, provided of course that a is greater than 0. Now the process will be repeated with either x1, x3 and x4, or x2, x3 and x4. In other words, one of the points is discarded and the remaining 3 are used. A new parabola is interpolated through those 3 points. The minimum of that parabola is found. Brent's method requires an interval AB in which to search and includes several safeguards to ensure that the method is likely to converge. Whenever you use an iterative method to find a minimum, convergence is an issue. It's always possible that the method diverges or just repeats itself, in other words, loops over and over. In MATLAB, the function fminbound uses a variant of Brent's method to find a global minimum of f between x equals a and x equals b. Here's how this works. We would like to find the minimum of the curve f, shown in black here. The minimum is over here. And we start with 3 points, x1, x2, and x3. And as you can see, f of x3 lies below f of x1 and f of x2. We then interpolate a parabola, shown in blue, through the 3 points x1, x2, and x3, and find its minimum. We see where that lies on the curve f. Then we discard the point x1 and we use the points x3, x4, and x2 and interpolate a parabola through that. And we find its minimum on the curve that lies there. And so we proceed. And as you can see, we have now moved from the point x3 to the point x4 to the point x5, getting closer and closer to the actual minimum, which is here. Let us now discuss the gradient descent method, which is a very powerful method for optimizing functions of one or more variables. For the purpose of illustration, we will consider here a function of just 2 variables, but it should be easy to see how to generalize this to higher dimensions. Suppose therefore that f of xy is a function of 2 variables x and y, and that we want to minimize the function f. The idea behind gradient descent method is very simple. Starting from an initial guess x, we move a small distance in the direction in which the function f is decreasing most rapidly. This brings us to a new point, where again we compute the new direction in which f is decreasing most rapidly and move in that direction for a bit. We iterate this procedure over and over until we cannot find a direction in which the function f is decreasing, in which case we have reached a local minimum. In order to find the direction of steepest descent, we need the concept of the gradient of the function f, which is a vector consisting of the 2 partial derivatives of the function. These 2 partial derivatives should be 0 at a local maximum or minimum. In other words, the gradient vector will be 0 at a local max or local minimum. Let u be a unit vector which represents an arbitrary direction in which we move. As u is a unit vector, its components, delta x and delta y, must be such that delta x squared plus delta y squared adds up to 1. We're now going to start at the point x, and we're going to find the direction in which f is decreasing most rapidly. Suppose we want to move a small fixed amount epsilon in the direction of the vector u. In other words, we want to move from the point x to the point x plus epsilon times u. The change in the value of the function f is then given as follows. The change in f, delta f, is just epsilon times df by dx times delta x plus df by dy times delta y. And if you look at that, you can see that the expression in brackets over here is just the dot product of the gradient vector with the unit vector. In other words, the change in the function f is given by epsilon times the gradient vector dotted with the unit vector. Now recall that the dot product of 2 vectors a and b can be represented as follows. A dot b is just the length of a times the length of b times the cosine of the angle between them. If we apply that to the equation over here, we see that the change in the function f is simply epsilon times the length of the gradient vector times the cosine of the angle between the gradient vector and the unit vector. Now observe that the function g of theta, defined to be the length of A times the length of B times the cosine of the angle between them, achieves a minimum when cosine of theta is a minimum, in other words when cosine of theta is equal to -1, which happens when theta is equal to pi radians or 180 degrees, in other words when A and B are vectors which point in exactly opposite directions. Thus the direction u in which f is decreasing most rapidly is exactly opposite to the direction of the gradient. In other words, it's in the direction of the negative of the gradient. In other words, the unit vector u is just minus the gradient divided by the length of the gradient. We divide through by the length of the gradient to make it a unit vector. Gradient descent methods now work as follows. We fix a parameter alpha, which controls how far we move, and an initial guess x0 close to the minimum. We now iterate and we keep moving in the direction of the steepest descent. So from the point x0 we move an amount alpha times the gradient of f at x0 in order to find a new point x1. We use the point x1 to find a point x2, a point x2 to find a point x3, etc. Under appropriate conditions, which may depend on alpha, the sequence xn will then converge to a local minimum of f. However, if alpha is small, convergence may take a long time because the step size, which is alpha times the length of the gradient, will be small. And if alpha is too big, the iteration may keep overshooting the local minimum and possibly diverge. Nevertheless, observe that as x approaches the local minimum, the partial derivatives df by dx and df by dy should both become smaller as well, and so does the total step size, alpha times the length of the gradient of f. Let's illustrate this method using an example. Consider the function f of xy equals x squared plus y squared. This function clearly has a unique global minimum at the point xy is equal to 0, 0. This is because x squared and y squared are both non-negative. The gradient is the vector consisting of the partial derivatives. The partial derivative of f with respect to x is just 2x, and the partial derivative of f with respect to y is 2y, and so the gradient is the vector 2x, 2y. Suppose we take the parameter alpha to be a quarter and we start at the point x0, y0 equal to 1, 2. Then x1, y1, the new point, is x0, y0 minus alpha times the gradient at the point x0, y0. And the gradient at the point x0, y0 is just 2x0, 2y0. And so the new point x1, y1 is given by the point a half 1. We then apply the same method to the point a half 1 and obtain a new point x2, y2, which is simply x1, y1 minus alpha times the gradient at x1, y1, and that will turn out to be a quarter half. Similarly, you can verify that x3, y3 is equal to an eighth a quarter, etc. And clearly this sequence is going to converge to 0, 0, the correct solution. On the other hand, suppose we choose the function f of xy to be x squared plus 3y squared, which also has a unique minimum at 0, 0. In this case, the gradient is given by the vector 2x, 6y. Suppose we take alpha is equal to half and we start at the point x0, y0 equal to 1, 1. Using the same method as above, we compute that x1, y1 is equal to 0 minus 2. Then x2, y2 is equal to 0, 4. x3, y3 will be equal to 0 minus 8. x4, y4 will be equal to 0, 16, etc. And clearly this sequence diverges, in other words, does not converge to 0, 0. We try to illustrate this here in 2 dimensions. It's not very realistic because in 2 dimensions there are only 2 directions in which you can move. You can move in the direction of the positive x-axis or you can move in the direction of the negative x-axis. But the idea is that you start on the surface, and if your alpha is small and you keep moving, you're going to move in the direction of steepest descent until you hit the minimum. And if alpha is really, really small, you're going to take really, really small steps and you're going to take a very long time to get there. On the other hand, if alpha is too big, you might move too far and keep overshooting the minimum and diverge, as we saw in the last example on the previous slide. So the value of alpha is very important, and you may need to play around with that when you implement this. We'll end now by discussing broadly the various optimization routines that exist. Basically, there are the following varieties. We have the direct search methods, which search a space in an intelligent way using only evaluations of the objective function and not, for example, the gradient, in order to find the local minima. The Nelder-Mead method is an extremely popular method for this, and it's implemented in the MATLAB function fminsearch. It basically works as follows. Given a function from r to the n to r, in other words an n-dimensional function, it starts off with n plus 1 many initial points, x1, x2 up to xn plus 1, which form the vertices of a so-called simplex in r to the n. For example, if n is equal to 2, we'll have 3 points forming a triangle, and if n is equal to 3, we'll have 4 points forming a tetrahedron. F is evaluated at each of these vertices, and these are then reordered so that the value of the functions goes from smallest to largest. Now, f of xn plus 1 is then the worst point, because we're minimizing f, and we want to move away from it. So we compute the centroid, which is essentially the average of the other points, the remaining points, and move in a direction in the line from xn plus 1 to c, away from xn plus 1. This algorithm contains various checks to judge how far one should move to get to a new point, for example, whether one should contract or expand or reflect, but we won't discuss these here. The process is iterative. But note that Brent's method, MATLAB's function fminbound, should be used for one-dimensional problems as it is more reliable than Nelder-Mead in one dimension. Apart from direct search methods, there are also gradient-based methods, and these use the gradient, in other words the vector of partial derivatives of the objective function, in order to decide how to move. We've just dealt with a gradient descent method, which is a steepest descent method. There are other variants of this, the so-called conjugate gradient methods, which are very similar, but will modify the gradient to ensure a better speed of convergence. Then there are quasi-Newton methods, which are variants of Newton's method in order to find a place where the gradient is 0. And a very popular method that works very well in certain cases is the so-called BFGS method, which can be implemented as one of the options in MATLAB's function fminunc. Here you will need to learn how to change the options of a optimizer inside MATLAB, as shown here. And then there are trust region methods, which are like Brent's method in that they approximate the objective function in some region, usually by interpolation of a quadratic, in order to choose the next iterate. This can also be implemented as an option in fminunc.